back when we talked about geometric power series, we said, okay, if we know the common ratio between subsequent terms, then we can determine the values for which power series would converge. So for example, if we know that the common ratio between terms of a geometric power series, suppose it were x is equal to, r is equal to x minus 1 rather, if we know that's true, we know that, okay, when the absolute value of this ratio is less than 1, we know this series converges, which allowed us to write what we call its interval of convergence. That is to say, we can write x minus 1 is less than 1 or greater than negative 1, which then we would clean up to write as x is less than 2, but greater than 0, right? So again, when for a geometric power series, if we can find its common ratio, we can find the values for which the series would converge, the power series would converge rather. So now that we've talked about the ratio test, we can now apply that same logic to say, all right, well, since we know the ratio test allows us to find the limit of the ratio between subsequent terms, we can then use the ratio test to help us identify the interval of convergence for a non-geometric power series. And I write almost in my notes because technically we don't actually have all the tests or all the convergence tests just yet to know exactly what's happening at every single endpoint. But we'll take care of that soon enough. We will go through all the convergence tests in just a bit. But at the same time, since we know our ratio test, we can say, all right, when the limit of our ratio is less than 1, then we know the series is going to converge for those values. And so we can come up with at least, at the very least, the distance between the center where the function is centered and the endpoint of its interval of convergence. That is to say, we call this the radius of convergence here. So in this previous example, even though I was using this to talk about a geometric power series, the interval of convergence here is from 0 to 2. We would say that the radius of convergence here is simply equal to 1. It's the distance from where the function is centered, which in this case, it was centered at 1, to its endpoint from 1 to 2. If I were to draw this out here, I would say something like centered at 1, it goes to 2, and then it goes to 0 here as well, right? So we're talking about this distance from the center to its endpoint. Now again, we don't have all the tests to be able to state definitively what's happening at 0, whether or not it's convergent at 0 or convergent at 2, but we will soon enough. All I care about in this lesson is making sure that we understand that the radius of convergence is simply half of the entire distance of our interval of convergence. Okay, so it's the distance from the center to the endpoint. So let's try an example. And actually, before I try an example, important fact that I should highlight here, that every power series, it converges at least at its center. So even when a series appears to be divergent, we can still say that it converges at its center. Its radius of convergence would then be 0, but it at least converges there. So we'll talk about an example like that in just a bit. So let's look at this example here, where we're going to use the ratio test to help us determine the radius of convergence for this power series here. So the first thing I'm going to do is I'm going to set up using the ratio test. So let's write that. So we're going to do the ratio test here. And we're going to say, okay, let's look at the limit as n approaches infinity of the absolute value of the n plus 1 term. So x minus 3 to the n plus 1 all over 2 times n plus 1. Okay, you could write this as 2n plus 2. It doesn't matter too much, right? 2 times n plus 1. And then we're going to divide it by the a sub n term, which means we're going to multiply by the reciprocal of that. So we're going to put 2n in the numerator and x minus 3 to the n power in the denominator. All right, now let's clean this up a little bit before we start thinking about for what values this would converge. So we know that in the x minus 3 to the n plus 1, that is 1 degree higher than what we have in the denominator here. So we can clean that up by dividing this into all of this. And all that would be left over is x minus 3. So I'm going to rewrite this, and I'm going to say the limit as n approaches infinity of the absolute value of x minus 3, sorry, I'm going to write this as x minus 3 times 2n over 2n plus 2. That there. Now, you'll notice that as I am taking the limit of this, I'm taking the limit as n approaches infinity. And so that x minus 3 is sitting there saying, wait, that doesn't affect me. So we can actually just move that to the outside, and we can write this as, we're going to keep that absolute value there, that absolute value of x minus 3 times the limit as n approaches infinity of the absolute value of 2n over 2n plus 2. And again, we're looking to see, when is the limit of this ratio going to be less than 1? That's when this series would converge. Well, just by cleaning this up a little bit, we know that all of this is going to be equal to 1. The limit of that ratio there is equal to 1. So what that allows us to do is kind of now write this as the absolute value of x minus 3 is less than 1. Now, I know this, some of you might be thinking, this looks like a lot of work for something that I was able to pretty quickly do with geometric power series, but the difference now is that this isn't a geometric power series, right? So now that allows us to write our interval of convergence tentatively as x minus 3 is less than 1, and this is greater than negative 1. And so this would be x is less than 4 and greater than 2. So this is tentatively, and I keep on saying tentatively, our interval of convergence, because at this time, I don't know what's actually happening at 2, and I don't know what's happening at 4 just yet. It could be converging at 2, in which case we would say this is less than or equal to. And it could be converging at 4, in which we would say this is less than or equal to. But we don't know that just yet. And actually, that's only partially true, because if we were to take these endpoint values, and this is just a little bit of a separate aside as to where we're going, if we were to take a look at these endpoint values and plug them into our a sub n, so for example, if I plug in 2 into this function here, I would actually get the following. I would say n is equal to 0, down up here. 2 minus 3, that's negative 1 to the n power over 1 over 2n. And I'm not going to show the whole conditions for convergence here, but using the alternating series test, we actually see that it does actually end up converging at 2 by AST. So this actually converges by AST. And if you want to think about that, pause the video and just check to make sure if that works. But by the alternating series test, it does converge at 2. And so actually we do know that it does converge at that endpoint 2. The 4 is a little more unclear right now, because if I plug in 4, that gives me, and I'm just going to copy this here. If I plug in 4, then actually I get 1 to the n over 2n. And right now we actually don't have the test to determine whether or not that converges. Spoiler alert, this actually diverges. This particular series diverges. So it turns out the entire interval of convergence is this, as it's written right now. Don't worry too much about the interval of convergence for a non-geometric power series. What I care about in this lesson is whether or not you are able to find its radius of convergence, which we can. By looking at the interval of convergence as is tentatively written, we know that our radius of convergence, or my ROC, is going to be 1. It's the distance from where the function is centered, 3, to 4. So our radius of convergence is equal to 1. Okay? So let me do a couple of more examples with you just to make sure that we are able to see the radius, find the radius of convergence with a couple of different power series. So number 13 is actually a really easy one. We already know, just by looking at this is actually a geometric power series. So we actually can find this even without discussing anything that we just did. We know that our common ratio is equal to 4x. So when the absolute value of our common ratio, so let me just rewrite that, the absolute value of our common ratio, 4x, when that's less than 1, then we can say this here as a compound inequality. So when x is less than 1/4 or greater than negative 1/4, this is our IOC again. That means our radius of convergence is the distance from the center to the endpoint, which is 1/4. So there's our radius of convergence there, okay? All right, now let's do something that's a little bit more in line with what we discussed today. Let's try number 14 now. So for number 14 here, let's look at this one. So we're going to apply the ratio test. The limit as n approaches infinity of, well, this is x plus 4 to the n plus 1 over n plus 1 times 3 to the n plus 1 times the reciprocal of a sub n, so n times 3 to the n over x plus 4 to the n. All right, so now ask yourself, is there anything that I can clean up here? Well, I know I can divide this 3 to the n by this into this 3 to the n plus 1 down here in the denominator. So I'm going to divide that and that. And similarly, I've got an x plus 4 to the n in the denominator, and the x plus 4 is being raised to the n plus 1 power in the numerator. So I can divide that with this. So now that we've done some division, let's rewrite our ratio on our limit statement. So the limit as n approaches infinity of, we have x plus 4 times n all over n plus 1 times 3. And we're checking to see when would this be. So what is the limit of this? What is the limit of all of this? Well, I'm going to move everything that isn't affected by me finding the limit to the outside. So that's x plus 4 in 3. So x plus 4 over 3. So we're going to take that. And we know then that the limit of the remaining terms, n over n plus 1, that is equal to 1. And so all we're left with is x plus 4, the absolute value of x plus 4 over 3 is less than 1. Okay? And since this was already the absolute value of 3, we actually don't need an absolute value around the 3 just now, but it's fine. I'll leave that in there. So what does that allow me to write this as? This is x plus 4 is less than 3, but greater than negative 3. X is less than negative 1, but greater than negative 7. Again, all we're concerned about is what is our radius of convergence. And so we know our radius of convergence here would be r is equal to 3. That's the distance from the center, which is at negative 4, to the endpoint, the center there, which is just going to be 3. Okay? Actually, all right. Yeah. So our center is at negative 4, and then we're going to negative 1. That would be 3. Yeah, that checks out. All right, just wanted to make sure. Okay, let me do one more with you all. Number 15. All right. So this is going to be a little bit of writing. I'm just going to give you a heads up right now. Just as a forewarning, there's going to be a little bit of writing here. So we have the limit as n approaches infinity. Let's do the ratio test. All right, here we go. Deep breath. N plus 1 factorial times x to the n plus 1 all over n plus 1 to the third times 4 to the n plus 1. Now we've got to multiply all of that. So I'm going to actually move this. Let me actually make this a little bit smaller. And now we're going to multiply that by the reciprocal of a sub n. So that's n cubed times 4 to the n all over n factorial times x to the n. Okay. All right, I think I got everything. So now let's see what we can clean up. So I've got a 4 to the n and a 4 to the n plus 1 down here. So that strikes my eye, so I'm going to divide that out. Same idea with this x to the n down here and this x to the n plus 1 up here. And just like in the previous lesson, we see some factorials now. So this n plus 1 factorial is equivalent to n plus 1 times n factorial. So I'm going to divide out that factorial symbol with this n factorial. So I think I've divided everything that I can, and if I miss anything, I can always take care of it in the next step. So I've got the limit as n approaches infinity of the absolute value of x times n cubed all over. It looks like I did miss something in the previous step. I notice I have an n plus 1 up here and an n plus 1 cubed down here in the denominator. So I could have divided this x to the n plus 1 with one of these n plus 1s in the denominator. So then now I can write this as n plus 1 squared times 4, and I think I got everything else from the denominator. All right, so now we're ready to clean this up. And again, anything that's not affected by us taking the limit, we can move to the front. So we can write this as absolute value of x over 4 times the limit as n approaches infinity of n cubed over n plus 1 squared. Now, we're checking to see when would this be less than 1? Well, hold on. We've got a bit of an issue here. What is the limit of this? Well, I see that the degree of the numerator is greater than the degree of the denominator. So as n approaches infinity, this is also going to be infinity. No matter how we slice it, that's going to be infinity. Therefore, this series actually diverges. So therefore, this series diverges. Well, if that's the case, then it would appear that for no values would this series ever converge because it's a divergent series. But go back to this important note that I highlighted above. We know that every power series converges at least at its own center. So where is the center of this particular series here? Well, we don't see anything like x minus 3 or anything like that. So we know that this series, even though it diverges, its radius convergence would be equal to 0. It's converging at its own center. Okay. Now the distance of the convergent values from its center to its endpoint would be 0 because it doesn't converge for anything else, but it converges at its own center because it converges at x is equal to 0. It doesn't converge anywhere else, so it's got a 0 radius, but we still would write that its radius is equal to 0. Okay. So again, I will have you work through the next couple of problems, check your solutions in classroom, and be ready to discuss in our next class.